Unit 2, the atom, Chapter 3. Chapter 3 starts beginning, kind of continues off where we left off, kind of using Bohr's model as a means to bridge the gap that we are going with this and moving on into some of the other ideas on what we can actually do and to kind of map the atom, so to speak. We know where the protons are, we know where the neutrons are, and it's just trying to figure out what information can we gather about the electrons. Schrödinger gave us a little bit more information into this idea of quantum mechanics. Erwin Schrödinger used these very intense calculations, be theoretical calculus, and for the most part we're not going to worry about it because that's math that's way above us. There's very few high school math teachers that would even begin to fully understand some of the math that was done. So we're not going to go into it. We're going to kind of use the conceptual of the what can we use to help us describe what's going on from a conceptual point of view. So we're not going to get into the math that explains why this happens. It's going to be, hey, this happens, these people said this, and so we'll go from there. Now, Schrödinger's model gives us a little bit more of a kind of a, hey, look, where are the electrons at? Well, based on Schrödinger's calculations, there is a high probability, meaning you're very likely to find an electron around or close to the nucleus. And that should make somewhat sense. That doesn't mean you're going to, it just means you have a high probability of finding one. It's like walking into a candy store and saying, you know, I might find somebody here, a kid in here because it's a candy store. And chances are you're going to see some kid walking around looking at candy and wanting candy. And that's just something that you're going to see because you have a high probability of it. As you go away from the nucleus, you find that you have less and less probability of finding an electron, and it should make sense. And that's why this image here, the coloring changes or gets lighter as you go away from the nucleus, as the likelihood of finding an electron is less. That doesn't mean you're not going to find one, it just means that you're less likely to find one. It's like searching for a needle in a haystack. You could find one, it just might be a little bit harder. Now, Schrödinger kept this idea of quantization from Bohr, but expanded upon it. One of the first things is that he talked about this principal quantum number, which we talked about as n, and the sublevels, orbital, and electrons within those. There are other letters and other distinguishes for them, but we're going to kind of, again, use a little bit more generalization for some of this. And if you wanted to worry about some of that, that is why we do have the high school chemistry class in this school. So the principal quantum number represents where the electrons are kind of located. It would be like the rings on Bohr's model. The row that the elements fall in, that's what we use. And we kind of talked about that in the last video, but it's the row of elements. So hydrogen is in row 1. That's because it has a principal quantum number of 1. Row 2 has a principal quantum number of 2. Row 3, 3, and so on and so forth. So the row numbers discuss what the principal quantum number is. Now, as the principal quantum numbers increase, the number of sublevels also increases. So if you have 1, n is 1, well, you have only one sublevel, and that's s. And if you look at the top row of your periodic table, you'll see that only hydrogen and helium are present in the top row. And that's because each sublevel can only hold 2 electrons, in some cases more. But for that one, the S can only hold 2. And so there's only 2 elements in that first row. Now, when n equals 2 and you start to see different things, you'll start to look at it and go, okay, n equals 2. That means there's 2 sublevels, S and P. Now, if you look very closely at your periodic table, right above lithium and beryllium, you'll see this little thing that says S block. And then above boron to neon, you'll see something that says P block. and then right above below that you'll start to see another one that says D block, and the other ones, the lanthanoid and actinoid series, they'll look at it as more of a F block. But we won't actually get into the F block. We're not going to worry about that. Some things get really crazy back down in there. But it's this idea that as the number of the principal quantum number increases, so does your sublevels. And it's kind of, for the most part, equal. And so one would guess or think that, well, okay, if you have a principal quantum number of 5, you would need 5 sublevels. Unfortunately, that's not how it actually works. In theory, they're there, but we don't need them based on how many electrons can fit into those sublevels, or how many orbitals are in some of those sublevels. And I might be getting a little bit ahead of myself in that. But it is important to kind of note that the order in which they go is S, P, D, and F. And so as you expand out, now S can hold 2, P can hold 6, D can hold 10, and F can hold 14. And so as you kind of look at this, some things might start to make some sense, hopefully, as we kind of explain through this how this all works. Again, little generalizations now, but the important thing is principal quantum number is 2, that has 2 sublevels. Principal quantum number is 3 sublevels, and so on and so forth. What is the lowest number principal energy level in which P orbits are found? Now, each sublevel has a number of regions in space. These would be the orbitals. So now we're kind of really getting away from Bohr's model. These orbitals are where areas or regions of space in which you have a high probability of finding electrons. So, and they're not going to be real nice looking things all the time. They're not the circles that many people think. They have some very interesting shapes. A lot of this comes through Heisenberg and his uncertainty theory, and it's the basically coming down to a simple fact of we're not really sure about some things. But Heisenberg and Schrodinger kind of went back and forth, and actually the Schrodinger that we're talking about is the same as Schrodinger's cat. And it's through his correspondence with Heisenberg that he actually comes up with this idea of Schrodinger's cat, which would be something that you can definitely look up and find some more information on later. Now, on Heisenberg's uncertainty theory or uncertainty principle, I've seen it. It says that the exact position and momentum of an electron cannot be known. It's kind of playing around if you use the idea of like a GPS. GPS is kind of guessing. If you look at use like Google Maps or something like that, or TomTom or Siri or whatever it is, and you look at yourself on there, and you can, like, as you're mapping it out, it kind of skips based on it's guessing how fast you're moving down the street. And that guessing is kind of what's going on here. Is they know what direction you're moving. They're not really sure about the speed, so they have to guess and, based on some calculations, see where you're at. Well, if they wanted to know how fast you were actually going, your location kind of gets lost in the mix. And so that's kind of what it would look like. If you want to know where an electron is, people would say, well, slow down the electron, and then you'll know where they're at. Well, that doesn't tell you anything about the speed. And then someone says, well, then just speed up the electrons and measure their speed. But you don't know where they're at then when they're going that fast, because they become much more random, and so there's less predictability. And so Heisenberg says, well, we know they're there. We just really can't tell more about them. And we want to, but Heisenberg says, yeah, you really can't. And so how do you know this? It's like, well, you can maybe try to use a photon, and it kind of uses this illustration here is that the photon goes and hits this moving electron. Well, that moving electron is no longer going to be in that location after the photon hits it, because it's going to bounce off, and therefore it's going to move the electron in a different direction, and that's where we use some more physics-based terms in talking about velocity and momentum, in dealing with vectors and some of those types of things. But it's not going to be in the same location. It's not even going to be in the same path anymore. And it's those things that kind of lead us to this idea that you might try to figure it out as best you can, but you knew there was one there, but you don't know where it's at anymore. So what these shapes look at, and again, we're using some high-intense three-dimensional theoretical calculus here. These are what basically it is telling us. An s orbital has what's called a spherical shape. It's in a three-dimensional thing. It would look like a sphere in it because it has 3 dimensions on it. Now the p orbital has p sublevel has 3 orbitals. We can see that the little dumbbells that they see here, you can see that it kind of goes in on the x-axis, and the y-axis, and then on the z-axis. That's what makes it three-dimensional. The z-axis would be the equivalent of it like popping out of your screen. They move it here so that it's a little bit easier to see that 3-dimension. Your x and y is usually, as you would see in math, there. Well, it's tough to draw sometimes for people, but that would be your z-axis on there. And so it's a little bit different, but they know that we have 3 orbitals there, and so there would be 3 places where we can put electrons. The d orbital has 5 of them, and it gets really crazy. If we look over here at the 5th one, it gets some really crazy, weird things happening. But we have a total of 5 orbitals that give us it's kind of a different shape, but it's kind of a little bit maybe a 4-leaf clover kind of a look, but it changes based on its orientation in space, around the x and the y axes, and so those are some of the things that do that. And then you get this one that's really weird. Don't worry about the x, y, z stuff. That's something denoted for a different class, but the images work really well. Not going to waste our time looking at the F block. We're not going to use the F block. If you really wish to see what the F orbitals look like, their shapes get very crazy looking, and you can look those up using Google Images. So what does this all mean? Well, it helps us to try and figure out a way to put together what are known as electron configurations. The electron configurations, they are a shorthand notation for describing where they are at. And our periodic table that we use has a lot of these things done. And so the first 2 columns, that's where it says is that would be lithium and beryllium, groups 1 and 2 all the way down. That's the S block. And so they're s orbitals. They might have others as well, but that's what at least they start with. Columns 13 through 18, that would be boron through neon. They're known as the p block, and because they have p orbitals in there, and so it's a little bit different. And p orbitals have 3 orientations, as we saw, and each orbital can hold a total of 2. That's where we get our 6, because 3 times 2 equals 6. Weird. And then we have our transition metals. That would be groups 3 through 12. That represent the d orbitals. And what that does is give us the 10 possible orientations. As we saw, there were 10 electrons there. There was 5 orbitals, 10 electrons. And so you can see each line kind of represents a number of those things. Well, we didn't talk about it, but the 14 would probably mean that there are actually 7 orientations in space. That's why it gets a little crazy. And so each dash can hold 2 electrons, and this is where you would see your 14. The S usually just has 1 dash for it, so that it only has 2. Before we get into actually looking at electron configurations, it might be very valuable to us to actually talk about the principles or the rules that regulate the how or why we have to do certain things. And the first one we'll talk about is the Aufbau principle, then we'll talk about Pauli's exclusion principle, and then Hunds' rule. Aufbau principle says that you have to occupy the lowest energy ones first. And earlier we talked about the electrons that are closest to the nucleus would have the least amount of energy. And that means that the 1s is the lowest one. And you can think of it as like a ladder. If you fell off the ladder on the first ring, it would probably not hurt real well. It probably wouldn't feel great, but it's not going to hurt a lot. The higher you go on the ladder, the more it's going to hurt. So therefore, you're going to have more energy when you hit that ground. And so we want to be very careful about how we kind of go through it. And the Aufbau principle kind of looks at that, is that you have the 1s, the 2s, the 2p, the 3s, 3p, and then something kind of crazy happens. Is a lot of people would guess, well, next would be 3d. But if you look very closely, and it is kind of tough to see, even with this image, is that the 4s is kind of just a little bit lower in energy than the 3d. To take this into account, we fill the 4s, and if you look at your periodic table, row 4 actually starts, the D block actually starts in row 4. And that's because you can use some things in that the D block, excuse the bell there, D block is actually n minus 1, meaning n is your principal quantum number minus 1. So if the D block is in row, say, 4, what D block is that? Well, minus 1 from that, and that would be 3D. If you had an element that was in the 6th row, getting really crazy there, 6 minus 1 is 5. So it would be in the 5D. So there's a way to kind of use that to our advantage. But we're not going to get anything. The most one we'll worry about is barium, and that would get us into probably, I think it's the 6s. And so we won't go any farther than that. The electron configurations for some elements differ from those predicted by the Aufbau principle because now Pauli's exclusion principle says that each orbital or dash can have a total of 2 electrons, but they need to be in opposite spins. These opposite spins meaning that one goes up, one goes down. Now the order, there is technically a very specific order. It does actually need to follow the up-down pattern, but I'm not going to worry if in another one you go, I'm so ingrained to actually write it that way, that I just automatically, but if you went down and then up, I'm not going to worry about it, because what I want to see from you is that they're an opposite spin. Whether one is up, one is down, doesn't matter. You'll notice, though, that in this example, we have up, down, and then in 2s, we have up again. And why is there only 1 in there? Why don't I just take that and move it over there? Well, that's because you can't. Because each dash can only hold 2 electrons. So we would look at this and say, well, there's 3 electrons here. Well, what element has 3 electrons? Well, that would be lithium, actually. Lithium has 3 electrons. And to get to where lithium is located, just like as if you were reading a book, you have to go through the 1s, fill it up, and then get to the 2s. Well, by the time you get to the 2s, you only have that 1 electron there to place. And so that's where the last electron goes. Now, Hunds' rule says some other parts, in that if you have electrons in the same, you can't, they have to spread them out before you don't. Actually, this image is incorrect. So you have to, the same direction, you have to kind of put them in. For some reason, this got split off here. Is you can't pair them up. If you have space, space them out. It would be the equivalent of saying, well, if you have rooms in a house, everybody gets their own room, unless we have to pair you up. So once you have to pair up, then pair up. And so this is what this image should look like. I don't know why that didn't happen. And so we have, that's what we say, we want it to look like this. Good. And then the other one is bad. And so we have pair them up at the lowest level first. Next level, well, I still have to pair that one up before I can start expanding out and going from there. Yeah, we'll look at some examples here in just a little bit that might help explain this idea a little bit better. Speaking of examples, let's try some out. Now, lithium ends, if we look at where lithium is at, well, it's in row 2. What block is it in? It's in this S block. Okay, that's where it ends. So that's what we write is 2s and then a line. Well, if that's where lithium ends, how do you get to 2s? You have to start with 1s. Okay, now I have to fill my electrons. I have to fill my lowest energy level first, which is 1s. And each line can have a total of 2 electrons, and they have to be in opposite spin, meaning one up, one down. Well, if lithium has 3 electrons, because its atomic number is 3 in this case, I have 1 electron left. Does it matter if it goes up or down into the 2s? No, but I'm going to put it up because that's, by all technicalities, what I'm supposed to do. Now, beryllium, some might be able to guess, like, well, I think I might know what beryllium is. Well, beryllium also is in the second row and in the S block. So that's where we end. Where do we start? Well, it starts in the 1s. What do I do? Now I have to fill my electrons. I have to fill my lowest electron first. So I fill my 1s. One up, one down. Then I still have 2 electrons. I can't just make lines up here. That would be wrong. So what I do is I have a filled 2s. Now boron is in the same row as lithium and beryllium are. But if you look at where it's located, it's in a different block. What block is it in? Well, that would be the 2p block. If we remember back on how many orientations there were for the p block, there were 3 orientations. Each orientation gets a line. How do I get to 2p? Well, drinking lots of water. Potty humor aside. Well, I have to start with 1s. Then 2s. And now I'm at where I should end. But I need to put my electrons in there. I don't go through and just write my electrons, spread them out, because I have 5 electrons and I can just put them in there. A lot of people think that that would be the right way to do it. But that's not it. We have to pair them up. The lowest energy level first. Because the electrons want to be in a lower energy state. And so we pair them up and fill accordingly. Putting 2 in the 1s, 2 in the 2s, and now the next level is the 2p. Where do I put it? Usually I fill it one individual way as I go across, as we will see in the next example. Fluorine. Where's fluorine located? Row 2. What block? 2p. So I know where I'm going to end. Where do I start? Have to start with the 1s. It's always going to be the way it is. Then I can go 2s. Well, I now have to start with filling in the electrons. Where do I start? With the 1s. And fill as I go. Now what do I do when I get here? Well, I'm going to fill this according like I should, spreading them out until I have to pair them up. Now that I have everything paired up, I can, and some people will do this though, is they will take and go, oh, I'm supposed to just put everything in there. Well, you have to be counting your arrows at the same time. So 1s would be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this last little one over here would have been 10. That would have been the great one for neon, but unfortunately that's not the one we wanted. Oh, look, more examples. So where is sodium located? Well, let's look at where sodium's at. Well, it's in the 3s. Well, that's so okay. That's where we're end. Oh, that's where we're going to end. Is in the 3s. How many orientations does the s have? 1. It's not very good s there. How do I get there? Well, I have to start with the 1s. Then I need to go to the 2s, then 2p, 1, 2, and 3. How many electrons does sodium have? It has 11, so I need to count my electrons as I add them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Now, could I have added all of those electrons in the 2p block as I went and just paired them up automatically? Yes, very much. You could easily have done that. And so that's something we can do. Now many books I'm going to use this as an opportunity to kind of transition into the other way, is these arrows are very difficult sometimes to write. And so in some cases what they do is they will use superscripts to represent the number of arrows. And so a lot of times if you look them up in a book, you're actually going to see 1s2, 2s2, 2p6, and then a 3s1. I prefer that students at least start with the arrows. You can use the arrows on your summative assessments for this unit, or you can use the numbers. I think there still holds value into kind of seeing the arrows so that you kind of see from a conceptual point of view. You can see it easily. It's very visual for us. Now aluminum is again in row 3, but it's in the P block. Well, that's where it's going to end. Now why do we sometimes use those numbers? Well, guess what? It gets really intense to see all these arrows, and so it can start to look a little messy. But regardless, we're going to start with the same and go with 1s, 2s, 2p, 3s, and now I need to fill in my electrons. How do I fill in? Well, the same way, up, down, and as you can see, I'm filling in the P all the way across as I just fill it, because I know I'm going to have to go all the way through. And then I started having to really pay attention. Okay, 2, 4, and 6 is 10, 11, 12, aluminum needs 13, and there I go. Sulfur is in row 3, P block again. This time I'm going to maybe transition and write these out a little bit differently and say, well, I know sulfur is going to start with that, so I'm just going to say 1s2, 2s2, 2p6, 3s2, and I know that gets me to 12. And so sulfur is 12, 13, 14, 15, and 16. Well, how many into this at that block? Well, it's 4. And so it is P4. And now you can double check yourself. Add up your superscripts. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. Sulfur's atomic number is 16. You did it right. And as you might guess it, argon is the last one, so it is going to have the nice 2p6, 3s2, 3p6. And so it will continue on through, and it gets easier and easier as you practice. Continuing right along, calcium is in row 4. Well, we know that's where it's going to end. Where does it start? Well, again, with 1s, 2, 2s, 2, 2p6, 3s2, 3p6. Well, after 3p6 comes 4s. Well, if I double check and I count, I'm like, well, I only need 2. Well, good, because that's how many the S can hold. Now, scandium, something happens. Now, all of a sudden, we get to scandium, and we go from that S back down to the D block. What happens there? Remember that the D block is equal to n minus 1. What row is scandium in? Scandium is in row 4. That means it's the 3D that it's in. So what do? We start with 1s. And so we start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I like to write them as you would see it on the periodic table. Well, after 4s2, after calcium, you get to scandium. Well, if my D's are 1 less than that, that means it's 3d1. And your D's are always 1 less than the row in which they're in. So it's, what D is it? It's the 3D. Not that it's shooting out at you or anything like that. Now you need to look at the next one, iron. It's also in the D block. It's also in the D block that's in row 4, meaning it's in the 3D block. But what does it start with? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now you look again and go, well, scandium is D1, titanium is D2, 3, 4, 5, 6, and so you would actually write for that one 3d6. Now let's get a little crazy here, and we'll add silver. And now silver really kind of can throw some things in the monkey wrench business. It's in row 5, therefore the D block is the 4D. You have to start with that 1s again, and so some people get really annoyed with this, and there's an easier way of doing it. It's called the noble gas configuration, but some people like it, some people don't. 2p6, and things don't change as we continue through this, as you can see. It's like a very nice repeating pattern. And once you can do barium, if you can do barium correctly, you should be able to do all of them correctly in theory. And so 4s2, and I drop to my 3d10, if you count all of them. Back to my p block, doesn't change, and that's p6, because I'm all the way out in row 5. That means I'm going to go to 5s, 4d, oh, should put a 2 on that, baby. And now something crazy kind of starts happening. And silver, actually, if you look at it, is just one shy. And it's technically you could have wrote 4d10. That's one way of writing it. I'm not going to worry about it. If you write 4d9, that's good. But all technicalities would actually say that the way in which it is supposed to be written is 1 and then 10. And so a half filled versus a full filled is kind of a little bit more stable, and that's what we want. We want stability when it comes to the electrons and those types of things. So as you're kind of looking at some of that, that would be the why. Some of these have some weird orientations. Some other ones that happen are around chromium and manganese and on down. They get to be some real weird ones, but we're not going to focus a lot of our time and effort on that. This kind of is a nice little image of what it all looks like. It doesn't take into account some of the exceptions that are out there, because if you Google the answers, they're going to give you the exceptions. I don't want you to worry about the exceptions, and so therefore that's kind of how I know whether or not you're just Googling up your electron configurations for your formative assessments. And that will come and hurt you again on your summative assessments. So you can kind of see and look at how this all breaks down. There is a pattern to it. I would actually suggest practicing enough so that this pattern becomes very easy for you. Isoelectronic, meaning you have elements or atoms that have the same electron configuration, meaning you've lost or gained electrons. And they do this. Actually, they do it fairly quickly and readily. And that's so that they add some stability, because they want to do something and fill that so that they can fill their octet, meaning 8. If you look at the s and p orbitals, you would see that the s and p orbitals add up to 8, because 2 plus 6 is 8. Therefore, you got an octet, because an octa means 8. And that's what they're looking for. They want an electron configuration of the s and p orbitals to have 8, what's called as the valence shell. The d orbitals and the f orbitals, they don't take into all that much into the valence shell. It gets kind of really crazy and weird on there. And so what we really just worry about is that valence shell. We'll really come back to the valence shell in Unit 3 when we talk about covalent bonds. So this idea of the octet is not something uncommon. And so they're trying to achieve an octet. Well, what group has 8? Well, that is the noble gases. That is the group 18, also known as group 8A. So what happens? So say sodium loses an electron. Well, if sodium loses its electron, and this is, I'll revert back to the dashes for this one, we know that sodium is in 3s. To get there, I have to start with the 1s, the 2s, then the 2p. Oh, starting to write some weird things now. And I'll just change that to, so 2p, 1, 2, and 3. Kind of weird dashes in there. So we see that happens, and so I'm going to write in my arrows that I should, and so we write our arrows in, and okay, I have that, they fill, and so I'll put them in there, and it gets really crazy inside here, but really messy. And so now I have 3s. Well, what happens if I lose an electron? Well, that's where using pencils work. You can just erase it. So I lost that one electron. Now it only has 10. What other element only has 10? Well, that would be neon. And so there you can kind of see how that works. The other method of doing that is to use a 2s2, 2p6, 3s2, 3p6, and if you wrote the 4s2 out, you're like, well, calcium's losing 2 electrons. Well, what does that mean? Well, you lose 2 electrons, and so we lost 2 electrons there, and we can see that the electron configuration for that is, as you can see, and it's actually the same as it would be for argon. Now, oxygen is going to gain 2 electrons. So what does that mean? Well, I'm going to go back again to the dashes, and so we can kind of see what that means. Well, oxygen is in 2p. So I'm going to write that out here, and go 2p, 1, 2, 3. And I'll have 2s, and I put my electrons in here. Well, here we go. I know I have this, and I know I'm going to have this. Now, oxygen normally has, put that in there, even though it doesn't matter. I want to hold myself accountable. Does have that as its electron configuration. But if I add 2 electrons, and I'm going to use red, and I know red usually means wrong, but I'm going to add them so it's a little bit more contrast here. Where did they go? They went into those 2 empty spots. Now, oxygen has the same electron configuration as neon. Now, fluorine is going to be a lot similar to oxygen, where it's going to have 1s2, 2s2, 2p. Now, normally has 2p5, but if you add an electron to it, you actually have to add the number, and so I erase the p there and make it a 6. And so it's added an electron. And so we can see now that it has the same electron configuration as neon. What? It's added an electron to have the same electron configuration as a noble gas. It has 8 in its valence shell. And when we look at again on our valence shell, those last 2 is all they're worrying about. They don't worry about the stuff in the beginning. They only worry about the last 2. Identify the element that corresponds to the following electron configuration. Write the electron configuration for the atom nitrogen. And there you go. End of Unit 2, the atom. I would suggest practicing your electron configurations a little bit more, seeing me if you have any help or need any help with them. Again, feel free to ask any questions on electron configurations or any of the information from this unit before you get going on your summative assessments.